Hi, and welcome back to the Low Level Devel channel's Gameboy Emulator series. In the previous video, we got the project set up and started with loading a cartridge into memory and doing some simple parsing on it. In this video, we'll start reading the instructions from the ROM and start setting up the code for CPU emulation. So let's get started. The first thing we're going to start with is the bus, because we need to start reading data from the cartridge. And we'll do all of our reading and writing via the bus. So if you remember, we had a read and write function, and this is the memory map. I'm just pasting it in. So for each section of the memory that you try to access, it's going to go for different peripherals and stuff. So let's start with the bus read. So bus read and bus write. And I'm going to add a utility here as well. No impl. So this is just, while we're during the development process, there's certain things that won't be implemented yet, and we just want to terminate the emulator when we get to there. So I'm just going to do an fprintf to std error. We'll say not yet implemented. And then we'll just exit. We'll give a exit code, say -5. Okay. So now in the bus, we're only going to handle the ROM for now. So if the address is, let's see, less than 0x8000, then we're going to return the cart read at that address, which we'll implement soon. And no impl otherwise. So right now we're just doing the, it's not a function, I don't need that. So right now we're just doing the reading from ROM. And for bus write, we can do the same thing, but we'll call cart write. And it might sound strange to write to ROM, but actually some of these cartridges have special instructions that get run whenever you try to write data to ROM. So let's see, cart write at the address, the value. And again, no impl otherwise. Okay, return, and there's the no impl. So now we need to go over to the cart and add these methods as well. So we'll just copy from this. We're going to bus read and just rename them to cart read and cart write. And let's go down to the bottom of our cart.c file and we'll implement these. And these are actually pretty simple, since we're loading all the ROM data into memory. We can just access those memory arrays. So say for now, let's see, for now we're gonna just use ROM only type supported. So we're not gonna worry about the ROM switching and all that kind of stuff yet. We'll get to that later. So right now we're just going to read that address of the ROM data. So, and since we're doing ROM only, there is no actual writing to the cartridge. Okay, so let's see, next step, we'll go into our CPU.h and set up some of these other headers. Let me go back to our pan docs. So these are the registers that we want to deal with. We have the AF register, BCDE, HL, SP, stack pointer, and program counter. Okay, so we just need to implement these in a context as well. So I'm going to create a structure. We'll call it CPU registers. And I'm just going to create one for each of the 8-bit registers. So AF, BC, DE, let's see, DE, HL, and then these two 16-bit registers, program counter and stack pointer. So we'll do a type def struct for our context as well, CPU context. Part of the context of a CPU, of course, is the state of its registers, so we're going to put that in here at the top. And a couple of the things we're going to have here. We have the fetch data that we fetch while grabbing a register. So we'll tag this as current fetch. Let's see, so we have the fetch data. There's going to be some things like the memory destination, which may or may not be set. A current opcode. And let's see, a couple booleans. Is the CPU halted, and are we in stepping mode? Because we might want to implement stepping through the CPU as well. Okay, so let's go back and create another header here. This one's going to be for the instructions, because we want to define what is an instruction. And I'm just going to paste this stuff in here, and then I'll go over it individually. So instruction has a type, a mode, addressing mode, a possible register 1, possible register 2, and a possible conditional variable, and parameters in some cases too. So to start, let's start with the type, I think. Let's take a look at the instruction set first. So here's our instruction set, the different opcodes. So if we take a look at, for instance, here's an increment B. So its instruction would be increment. And let me take a look at some actual code. This is what a simple program would look like. For instance, here at address 0x100, we have a no op, then we have a jump operation, jumping to 0150, and now down at 0150, we'll have an XOR A, a load C, and then the value 10, and a decrement B. So these are the different operations that would run. That's what a program would look like. Let's go down here and just kind of see the different fields that would be involved. So starting off, our program counter is 100, the A register is 01, the flags register is set to the Z flag set, H and C flags set, and then the B and C register is 0013. So our first instruction would be the no op, which is 00. You see 0, 0. That is the no op instruction. No op essentially does nothing. So now it'll move to the next location, which would be one more. So it's 101. And that's where we find this jump instruction, which is C3. So if we go back and look at C1, 2, 3. We have a jump instruction which takes a 16-bit address. So it should be the C3 followed by 2 bytes. So it's 3 bytes total for the length of this particular instruction. So we have C3 and then 50 and 01. This is the equivalent of a JP 0x0150. Let's make this dollar, because usually you'll see dollar when you're looking at some assembly code for this. Okay, so that would jump to this location, 0150. And all of our registers here are still in place. You can see right down here at the bottom all these dashes. That means none of the flags are supposed to be changed by that instruction. So flags will remain as they were previously. So then our XOR A, if we look down at that, it's a F, Yeah, XOR A. You can see that one, the Z flag can be set. All the other flags are set to 0 after calling this. So, and it's 1 byte. So it's an XOR done on A with A. XOR done on L would be done with A as well. So all these XORs would be done with the A register and whatever the register that comes after it is. So XOR A, that's going to jump to the next program counter value will be 151. A is now 0 because we XOR'd it. The flag's 0 flag is now set, and then the others are cleared out because it said to put them as 0. Okay, now moving on to LDC, this should actually be 0E followed by 10. So let's see, LDC in 10 would be what the source code would look like. So if we look at 0E, you can see none of the flags are changed by a load instruction. So they all stay the same as they were previously, and since it's 2 bytes, we move on to program counter at 0153. And since we loaded into C the value 10, you'll see in our BC register, it's now 0010. Now moving on to our next one, decrement B. Let's see, that's going to be, let's take a look again, 05. So if we look at 05, we have decrement B. So with that one, the Z flag can be set. The null flag will be 1, H can be set, and then the carry flag is not affected. So let's take, and that's 1 byte as well, because it's specific to that one register. So of course after that we went from 3 to 54, 0. Now you'll see all the flags have changed. B is not 0, so the flag for that, for the 0 flag, does not get set. But now it goes down to FF. And that's just because of overflow, it rolls backwards. Okay, so you can see the flags have changed. We have B is FF and C is 10. Okay, so this is what the operations will look like inside of the CPU when you're running these instructions. So let's start working on an implementation for these. Starting with these registers, let's actually go back to the instructions. So you see what instructions actually look like. So let's take a look at these different enumerations. We have the type, of course. That's going to be the simple things like, is it a no-op instruction or a load instruction or increment or decrement? Okay, and there's a jump. And then these ones down here, special CB instructions they're called, which we'll get to later. Okay, so after the type, there is a mode in which you fetch data for that instruction. So I call it the addressing mode. So let's, for instance, if you have a load instruction, let's take a look at, let's say, load C D8. That's going to need to load into a register from a value that it reads D8. So 8 bits into that one register. These are a bunch of load instructions here that are register to register, so loading from one register to another register. Let's see, some more examples. Okay, loading a 16-bit value into a 16-bit register. So in that case, we would have to read 16 bits from the file. So these are all read differently. So in this one, we read the values from A and put it into the address of BC. So that's why it's pretty important to specify how you're reading the data for these different instruction types. So for this specific addressing mode, there's several different types. See, AM. So what I have is addressing mode D16 into register, register to register, then register to the memory location of a register, and one for a simple, just single register, one for a D8 value into a register. So these are all going to be important when fetching the data for an instruction. Then register type, these may or may not be used. Some these instructions will use them, some won't. Starting off, of course, is none. That means there's no register needed. Then we have one for each of the 8-bit registers and one for each of the 16-bit registers. Okay. And we have register 2 as well. And then we have conditions. Most of the cases, there's not going to be any condition. But in the case of some, such as jumps, you have, let's take a look at, for instance, a JP. There's a JP NZ, so jump if the 0 flag isn't set, then jump if the carry flag's not set, call if the Z flag's not set, call if carry is not set. So some of the instructions will have those kind of different options, and then the parameters just for these special CB instructions. If you look for C and B, you'll see prefix CB. That means it'll be followed by 1 byte that contains data to let you know which of these different instructions to process. We'll get into more of that later. Alright, so for now we have our basic instructions set up. Now let's add that to our CPU context. First I'll include the header. Alright, so now we'll say instruction cur inst. We'll make that a pointer as well. So now, let's see. Now let's create an instructions.c file. Add some includes here to start off with. So now I'm going to have an array of all the different instruction types. So okay, its size is going to be 0x100. And we're going to define these in line with the values. So we'll have the type and then the mode and whichever other fields are actually needed. In a lot of cases, type and mode will be just all that we need, really. So let's start with, let's go to instructions.c. Let's see, if we start with a no op, that's a simple one. So we'll define that, and that one's going to be at 0x00, and it is going to be an in no op, and then implied for its addressing mode, because there's nothing needed special to read after that. So now we'll do C3. If you remember, that was the jump, so we'll do INJP. And then the addressing mode, that was reading a 16-bit address. So we'll do addressing mode, just D16. And then AF, that was, I believe that was, the XOR. And it's just using a register, and the register type is A. Hopefully you're following this. We're just inline defining these structures. 0E, that was the load instruction to load C. So load, addressing mode will be register to, or D8 to register, and then the register type is C. And I'm just kind of adding these one at a time randomly. We'll add them as we hit them when running it. Eventually I might just paste a bunch in there to make it easier, but kind of want to go over one at a time for now. So the 05 was the decrement B, so decrement Addressing mode is just simple register, and register type is B. So we'll eventually fill these all out. I just want to do a few at a time to start with. Now let's jump over to our CPU.c, and let's define our context and a few other things. So we're just going to start by, let's remove this error message. Now we'll say if not, actually let's define our context first. CPU context CTX equals 0. So if not, CTX.halted. So if we're not halted, let's see, we're going to do a few operations here. The first is fetch instruction. Then we want to fetch data for that instruction. Then we want to execute that instruction. So that's going to be the typical things that happen during a CPU step. The fetching and then executing. So we'll create a fetch instruction function, fetch data, and an execute. So starting with our fetch instruction, first thing we're going to do is read the next opcode from the bus. And where on the bus do we read it? Let's include bus.h. We of course read it from the ctx.regs.pc. So we want to read it from the program counter and increment the program counter in the processed. Alright, so now we'll say our current instruction is, and we'll go back to our instructions.h file because we want to add a function to say, we'll call it get instruction, or we'll just call it instruction, instruction by, I guess by the opcode, right? Yeah, so instruction by the opcode. So it'll take in the opcode, and let's copy this and put it in the instructions.c file. Alright. So all this is really going to do is return the address of the instructions at opcode. And we could do some special error handling too. Actually, let's go to type. I want to add a default type is going to be, because right now if you don't have anything set up, it's going to think it's a no op. So I'm going to add the 0 value to be none. So then we can, let's go back here. So if I try to access 01 right now, its opcode should be none. So we can check for that. Say if that dot type equals in none, then we know it's an error. Let's say maybe return null. Then we can check for null when we invoke that function. So current inst equals instruction by opcode, and then just ctx cur opcode. And that should be all there is needed for the fetch instruction. I guess we could do some error handling there, but we get to that later. And for fetching data, now we want to fetch data differently based on a couple of things. First, let's set these individual fields. Mem destination is 0, and destination is memory is false. I need to actually add that as a boolean up here, because we might be writing to a memory location. We just need to carry that information around with us. So now we're going to switch the current instructions addressing mode. So in the case, for instance, of address mode implied means nothing needs to be read, so we just immediately return. And now in the case of register, so that would mean we need to read data from a register. So we'll set the context fetched data equals CPU read reg. And it'll be the reg type is the current instruction reg1. And this hasn't been implemented yet. We'll implement that in a few minutes. So let's see. Then we want to return. We do a couple more of these. Addressing mode R to D8. RD8. So we'll just do a case AMRD8. So it means we need to take 8-bit value and transfer it into a register. Alright. So that means we're going to fetch the data from the program counter. And we need to increment the cycles in the emulator. We'll get into more of that later, but for right now, let's just say that's one CPU cycle for reading the bus there. Alright, CPU read reg. So then we'll say regs.pc++ and return. And then let's see, AMD16. Okay, so case AMD16. So in this case, yeah, let me put some curly braces because I'll need some variables here. So we can only read 8 bits at a time. So if we want to read a 16-bit value, we need to do is read the program counter. Say some cycles happened. This is just for synchronization. So we're reading the low value and then we're reading the high value. regs.pc +1. Okay, then more cycles. And now we say the fetched data is equal to low ORed with the high shifted over 8. And hopefully that makes sense to you. We're shifting the high byte over to the high part of the results. And then we increment the program counter by 2 and return. So yeah, this we can get more into shifting later if you guys need help with that. You can talk about it in the Discord server as well if you don't totally understand all the byte manipulation. Okay, so that's it for our addressing modes, at least for the initial few. Of course, we're going to hit more that we haven't implemented yet, but for now in execute, we'll just say not executing yet, because we just for now want to fetch these things and be able to show that we fetched them and read the data for them. Alright, we'll also add a default case. Let's say we'll just error out unknown addressing mode. And I'll just copy this. And just return. Actually, let's exit as well. So that would be a fatal error. Okay. So I think we got the basics of those set up. We can also do some error checking here. So if the current instruction is null, we'll just exit as well. Unknown instruction. And we'll put ctx.current opcode. Let's also add this CPU cycling. EMU cycles int, say the number of CPU cycles. Eventually we're going to use this to synchronize our PPU with our timer and the CPU and all that. For now, I think I'll just do an empty implementation because it's not important yet. We'll get to it more later. Let's see, to do. Okay, yeah, let's see if we can build this now. Oh, CPU read reg, we need that as well. So let's create a new file, cpuutil.c. Going to include the cpu.h, and I'm just pasting this implementation. Essentially, we're switching through here based on the register type passed in, and then also a reverse function for that. So based on the register type passed in, we're going to return the register. And this reverse is really just reversing a byte. So you're taking these high byte, shifting it over to the right 8, and then taking the low byte, let's put 0, 0 to make it more noticeable, low byte and shifting it to the left 8, and then ORing those two together. So we're using that so that we can return the full values for the AF, BC, DE, and HLs. And I can explain that more on Discord if you have questions about it. Okay, the bus looks good. Yeah, I think we should be ready to try to build it. Let's make, and of course I probably spelled some things wrong. Let's take a look. That shouldn't be byte. So let's see. This should be U8. And fetched data. Yeah, I think I just spelled that wrong. But I think fetched sounds right. So yeah, fetched data, can't find it, so that means I just spelled it wrong. And there you go. Yeah, just rename that. Maybe just clear it and try to build again. Looks like still some issues. I guess I missed the header here. Instructions at 8, U8. Instructions by opcode. Let's see. Alright, these are warnings. I like to get rid of the warnings just to make it easier to see when there's errors. And yeah, let's just go back, and EMU cycles is already there. That's correct. So in CPU at the top, I think we just need to include emu.h. Clear and make ctx.reg. Do that wrong. Did I miss this part showing? Yeah. Let's go to CPU util, extern to CTX. There we go. Yeah, I just needed to add that as an extern. Make. There we go. Everything's built well. Let's see if it actually works. Alright, we'll start it on, let's see, do it on CPU instructions. Okay, unknown instruction 3C right off the bat. So that's not too good. me redo how I'm putting this information in here. Let's see. So inside execute, let's just add some debug stuff like executing instruction. We'll put the opcode for the instruction. Let's see, that would be ctx dot current opcode. Okay. And yeah, actually let's put the program counter in here as well, just so we can see that that moves. Put it right here, PC04X, and we'll say ctx.regs.pc. So let's make that, run it again. That didn't help. Let's try a different one. Mem timing. Okay, that one I see. Yeah, here, let's take this CPU step and return true. Remember, by default, it was always returning false from CPU step, so it would exit. So let's run it again. So now we saw it's executing. Yeah, let's put a tab before that. Makes it a little easier to see. Okay, so here you go. As you can see, the program counter just keeps going up and up and always reading that 0 byte. It shouldn't be starting at 0, 0, 0, 0. It should be starting at 0, 100. But I think at least we can see for now that it's reading the instructions. Let's see, we can actually go in CPU init and say ctx regs.pc equals 0x100, which is the entry point. So when you init the CPU, it sets the program counter to the entry point, which is the right thing to do. And let's go ahead and make that again. I'm going to rerun it. And there you go. You can see it. Program counter is 101 and then 104. So let's actually go back up to here. I'm going to move this out of the execute function. Put it down here before execute. And let's grab the value of the program counter before we do the fetching, before it gets updated. And then we'll use that value when we print this out, so it's a little clearer. And I think that's enough for now. So let's go ahead and make this. Okay, and rerun. And you can see it's at program counter 100, it read the 00, and then at 101 it read the C3. And that sounds correct, and unknown instruction CE, which is fine because we haven't defined that one yet. But I think that's a good start for this first video. I don't want these to go too long. I actually have most of the stuff for the next video done already. I just need to do the recording for the voice over it. But I think this is a good start. Let me know if you have any questions. Again, there's a Discord channel where there's a lot of good discussion going on, so you can learn more there, or leave comments. And of course, if you like the video, like, comment, subscribe, and all that. And thanks for watching.